Welcome, everyone. Thank you for joining us for today's webinar hosted by the NIH-funded Mobile Data to Knowledge Center, also known as MD2K, based at the University of Memphis. My name is Vivek Shetty, and I'm the MD2K's Training Core Director. Today's webinar on the MD2K's mCerebrum platform will be a tag team effort by our Chief Software Architect Tim Hnat and Syed Monowar Hossain, our lead software engineer. Both Tim and Monowar have been the main drivers and architects of the mCerebrum platform developed by MD2K. Today's webinar is the first of 3 webinars that will introduce you to the mCerebrum platform, and Tim and Monowar will demonstrate its various capabilities. Just a little housekeeping before we get started. A recorded version of this webinar will be available on the MD2K's mHealth hub. To access, you need to go to md2k.org. If you have any questions during the presentation, please type them into the chat box in your BlueJeans control panel. We will also have time for questions at the end. Please ensure that your microphone and video chat feeds are switched to mute to minimize any echo. So with that said, I want to welcome Tim and Monowar, and you guys can take it from here.
Thank you, Vivek. So I am Tim Hnat. I am the Chief Software Architect, and I have Monowar here with me, who is primarily responsible for the mobile platforms. Today, we're going to introduce mCerebrum and how to enable the development and field validation of mHealth biomarkers and interventions. So this, as Vivek said, this is the first of a series of webinars where we're going to show you how to get started with mCerebrum. Then, over the next few months, we're going to follow this up by covering how to set up the system to conduct a study. And then we'll conclude that series with a dedicated webinar targeting how to analyze the data generated by mCerebrum. This particular analysis will focus on our cloud offering, Cerebral Cortex, that will be available later this summer. So all of the details that we present here will be available on our website and in online documentation in the future, as well as this presentation being archived. So just as a brief overview of what we're going to talk about today, we'll look at the overview of mCerebrum, followed by a demonstration of this platform running on a smartphone, and concluding with a deeper dive into some of the interesting and unique features and contributions of the platform. So back in the 1980s, the US government opened up the GPS system for civilian purposes. This opened up the door for a new type of sensor platform. But knowing where you're at on the planet's surface is not really that useful by itself. And this information was eventually fused with maps to provide navigation assistance while driving a vehicle. As this technology advanced, GPS data became more tightly integrated, and with the release of the smartphone, we began to see interventions incorporated into the navigation system. So as an example, my current phone now understands where I live and work, along with when I typically travel between these locations. And it also understands my preferred route. It automatically provides interventions and alerts to me when there are significant delays that I should know about, and could therefore I can make alternative decisions, different route plans, or even stay at home a little while longer to avoid sitting in that traffic. So this is just one example, shows how a single new sensor, in this case GPS, can add so much new information to this world. But what just happened was many years of discovering what we can and can't do with this data. So as another example, it's kind of more closely related to mCerebrum, that is Fitbit. So this utilizes a simple multi-axis accelerometer to collect data. This in turn is transformed through a discovery process into biomarkers, such as step count or sleep patterns, or even various exercises. So this is accomplished by iterating on algorithms that transform sensor data into biomarkers. These devices then expose these biomarkers to a smartphone over a wireless channel, where interventions such as prompting a user that he or she has not reached a predefined step count, or by offering suggestions to improve sleep. In both of these cases, these systems went through an iterative process from sensing to analyzing to interventions. So mCerebrum allows us to take these mobile sensor platforms, such as mobile phones, smartwatches, chest bands, or even smart eyeglasses, and target various exposures, whether I'm at work or at home, I'm eating in a restaurant, I'm stuck in traffic, or I'm buying tobacco products. Then they're coupled with various biomarkers, such as I'm sitting too long, I have back pain, I'm overeating, I'm in some sort of heated conversation, or it's drinking, or it's drug use, or it's smoking. Any types of these behaviors we can target. Ultimately, there are some outcomes that we want to engage, or the outcomes that result from this, that we want to potentially influence. So the exposures influence the outcomes, and we'd like to either minimize, eliminate, or even promote those types of behaviors and those outcomes. These can include maybe stress reduction or heart failure management, or in another context, improving oral health behaviors by monitoring how you brush your teeth and encouraging that behavior. So each of these require us to go through the sensors to markers to interventions development process. So mCerebrum provides those capabilities to facilitate the entire process of discovery and validation of biomarkers and interventions, both in the lab and in the field. So the reason that commercial systems only provide biomarkers is that they've already gone through the sense markers intervention process, which allows them to only expose that biomarker data. This provides limited value for biomedical researchers due to the reliance on generally proprietary algorithms or unknown algorithms that compute the biomarkers and the limited amount of data that can be generated. So in a typical example of a Fitbit or a smartwatch, that might be hundreds of samples per day. But the development and validation of new mHealth biomarkers requires conducting research studies in the lab and field settings and collecting of raw sensor data with appropriate labels, such as through self-reports. This raw sensor data is increasing interest to research studies as it significantly increases the useful life of the information collected. Similar to how biomedical studies often archive biospecimens in biobanks, so they can be reprocessed in the future to take advantage of various improvements in biomedical discoveries, not possible at the time of data collection. Raw sensor data can be used to obtain new digital biomarkers that were not available at the time of data collection. Doing so, however, requires a mobile phone software platform that can be used to collect both high-rate raw sensor data and the associated labels in the field. mCerebrum supports this high-frequency raw sensor data collection in excess of 800 hertz, or over 70 million samples per day, along with the curation, analysis, storage, and upload to a cloud system. Because it must work in resource-poor settings, several of our current studies are with low-income participants. mCerebrum was built to operate the entire sense, analyze, act pipeline locally, without a constant data collection. To meet these needs, mCerebrum has 9 key capabilities. First, we support concurrent connections to a wide variety of high-rate wearable sensors, with the ability to add new sensors. It ingests a large volume of rapidly arriving data for which native support does not yet exist in the smartphone hardware or operating system. It quickly analyzes incoming data to monitor for data quality problems so that errors can be corrected. Fourth, reliable storage of quickly growing sensor data is critical, and whose archival is crucial to the development and validation of new biomarkers. Fifth, we need to control the interruptions to study participants, either through self-report or ecological momentary assessments or interventions. This is to limit the burden and cognitive load placed on them while still satisfying the numerous study constraints. Sixth, it should support the Sense, Analyze, Act pipeline for high-rate streaming sensor data applications. It should allow seamless sharing of streaming data from multiple sensors to enable computation of multi-sensor biomarkers, We use this in the context of stress, smoking, and eating behaviors. Architecturally, it should be scalable to support concurrent computations of these biomarkers without saturating the computation capacity or the battery life of a mobile phone. And then finally, it should be a general purpose and extensible platform that supports a wide variety of sensors, biomarkers, and study designs.
We investigated several existing platforms to fulfill our previously mentioned 9 key requirements and capabilities. Among them, Google Fit and HealthKit mainly target a consumer audience, which is different from ours, collecting high-frequency data for research purposes. And these two platforms are suitable for low-frequency data such as step count, blood pressure, or calorie count. The Open Data Kit supports wearable high-frequency sensor data collection, but it doesn't provide facilities to share biomarker data among applications. The AWARE framework can be used to conduct studies to collect phone sensor data, but it doesn't have any native support to collect high-frequency data from wearable sensors. None of this framework considers the assessment of user burden when triggering surveys or interventions, and real-time data quality assessment, which is essential to correct sensor placement in the field environment to improve the quality, improve the amount of usable data collected. Now, let's look at how mCerebrum looks like and its functionalities. So this is the general user interface for mCerebrum. Right now, I'm going to, we installed all of the required software, and we use AutoSense chest sensor and 2 motion sense band to collect the sensor data. It also collects the it also measures the stress events, and it has the capability to trigger the EMA in real time. So first, if I start the study, whenever I click Start Study, this screen will appear, and we see that at the very beginning, it asks us to start the study with notification. So whenever we click Start Day, that means the day is started, and it tries to trigger EMA whenever it is appropriate. The top part is the sensor data quality, which actually shows the data quality for each of these sensors. So if we look at these things, we see that the breathing pattern and heart rate, those are good quality of data that we are getting. The left wrist sensor is turned off, and the right wrist sensor, the data quality is good. Now we can visually check how the signal looks like. So if we check the heart rate sensor data, immediately we will see, yes, there are some ECG data that is collected by the system, and our peaks are clearly visible in this signal. And similarly, we can also check the breathing pattern. Like if we check the breathing pattern, then if I take a deep breath, immediately one survey appeared, that is a stress related survey. So most probably I am stressed. That's why the stress EMA is triggered. So I can start the survey, and it will ask me one question. I'll say mostly yes. And after completing this EMA, it will provide me some incentives. So this is one feature that after completing one EMA, it will the incentive will be given to the participant if the study requires that option. So I'm going back to main screen. So here actually the first part shows us which sensor data is collected properly and where the data quality is good or not. There is another option that the participant may provide the self-reported event, like if they smoke, they can provide any self-reported event from here. Another option is if the participant doesn't want to share their data at any time, they can turn on the privacy mode. Suppose if they think that they are not going to share any data related to chest sensor, they can click it, and they can also mention that around 5 minutes they don't want to share any data. It shows that the data is not collected, although the data quality seems that it is also collecting the data, but after some time the data quality measurement will understand that there is no data available, and it will show as cross. So just within a few seconds it should be red cross for both breathing and heart rate sensors. And we see that yes, the heart rate data is not collected. So if we again see in the plotter, we'll see that there is no data that is collected. So this is one opportunity to the participant that if there is any reason that they don't want to share the data, one option is they can turn off the system so that the phone cannot get the data. But we provided one option, like the participant can select by themselves that no, I don't want to share my data at this moment. And after 5 minutes, the data collection will be resumed again. But participant has another option that at any time they can say that no, it's time, I can share my data again. So if you see, immediately the data is captured again and it shows that it is okay. So this is a brief summary of how the mCerebrum works. So one of the key features of mCerebrum is its flexibility and configurability, which allows us to easily adapt and modify it to suit the needs of many studies. Currently, 6 different studies are actively collecting participant data, and another four will be started soon. The major difference among this study is some of the studies use different types of sensors, different types of biomarkers or triggering rules for EMA. So for example, in the Northwestern study, the micro-randomization technique is used to deliver intervention after detecting the stress likelihood of the participants, whereas in Rice study, survey questions are delivered based on stress. But in Ohio State study, the participants are asked to measure blood pressure, weight through Omron sensors, which is a part of congestive heart failure monitoring study. In total, our platform will be utilized by more than 2,200 participants and collect over 100,000 person days worth of high frequency sensor data. This results in over 4.7 trillion individual data points, which requires approximately 100 terabytes of storage. So what are the sensors that the mCerebrum currently supporting? mCerebrum supports a variety of wearable and wireless sensors to collect data from in the field. Our custom sensors were developed by Dr. Emre Artin at the University of at the Ohio State University, and include motion sense wristband that collects accelerometer and gyroscope data and pulse data continuously throughout the day. AutoSense to measure heart rate function via ECG and respiration through a chest band. The EasySense, which wirelessly measure heart function and lung fluid. mCerebrum also supports various commercially available sensor platforms such as oral beetroot brush, Omron blood pressure, and Omron weight devices. It also can collect the data, sensor data from the smartphone. Finally, it integrates with smartwatches such as Microsoft Band and wearable devices. These watches also enable mCerebrum to deliver notification to alert the user about something in the system, such as it is time to complete a survey. Due to the modular nature of mCerebrum, adding additional sensor platforms requires only implementation of a driver application to transform the sensor data into mCerebrum format. However, one should aware about the cost of adding this arbitrarily several sensors, because sensor data collection is the most power consuming part of the system. So using two different the main power consumption is due to the radio platform of the phone. So for example, two wearable devices with same radio platform perform better than one if we use same radio platform for two wearable devices, that is better than two different radios if we use two different radios for two different devices. mCerebrum provides the ability of examine the signal as we see in the demo. So in the plotter, if we select motion sense sensors, gyroscope signal, then we can view the signals in real time that will provide us whether the data is collected properly or not. We also see in the demo that the data quality assessment is available in real time. It's challenging to get a good quality of data for wearable sensors in a field settings. There are several failure points, such as user doesn't wear the sensor properly or forget to wear the sensors, or maybe the sensor is off, or the battery of the wearable sensor devices may be depleted. So the data quality assessment help us to identify help the participant to identify why the data is not collected properly. In this example, the respiration data is the respiration signal is indicating good quality state, but ECG sensor appears to be disconnected or not attached properly, and user interface shows the bad quality of signals. But it indicates that the system still receives the data, but the data quality is not good enough to analyze any biomarker computation. The risk sensors is showing that the signal is unavailable and it indicates cross. The real-time data analysis, data quality assessment helps the user to identify problems by visually inspecting the sensor data on the smartphone.
So real-time biomarker computation is one of the key features of the mCerebrum platform. These 6 biomarkers, stress, smoking, cocaine use, eating, craving, and conversation, are features the platform intends to compute on the phone. The first 2 are fully implemented, with the others being works in progress. There are several challenges associated with computing biomarkers in real time on a smartphone. First, data must be computed in a batch manner to limit both the CPU and memory requirements of the algorithms. And this is coupled with study requirements that many biomarkers should be computed as early as possible to allow for the best possible temporal locality for potential intervention. This batch process allows the platform to more efficiently compute the biomarkers, thus reducing the energy requirements. However, because of the batch processing nature of the computation, these algorithms have to be modified from their offline reference implementations, and decisions about how to handle operations that typically occur in this manner, such as the utilization of percentiles for normalization, or even looking ahead in time relative to a data point as part of the biomarker computation. So currently our computations, stress and puff marker, take about 15 seconds each minute on average to compute both stress and smoking biomarkers. This is running on a Samsung S5 phone. So let's use puff marker as a way to illustrate a typical biomarker computation pipeline to show why these computations can take significant amounts of time. First, data is acquired from raw sensors to be screened for good quality signals and cleaned of noisy or missing information. This is then utilized for time series pattern mining before possible candidates are identified. The next set of stages involves the classification of identified candidates based on a pre-trained model. A final post-processing state ensures that outliers are removed, further cleaning up the data set before it is finally constructed into a smoking episode. In our experience, most biomarker computations follow a similar approach, but simply generating real-time biomarker outputs is not sufficient for field deployments. The system should react to these events. This figure provides an illustration of what that data looks like for a smoking episode. The cyan dot right in the middle of the screen indicates the start of an episode that PuffMarker detected, which is supported by all of the yellow dots indicating potential cigarette puffs. In this case, a participant provided a smoking self-report at the end of the episode as indicated by the vertical dashed line. And the green shaded area shows the likelihood of a smoking episode as we progress through time, as determined by our biomarker model. This particular instance peaks at about 95% likely. These types of biomarkers can be used to trigger EMAs or confirm refute prompts elsewhere within the system, and thus engage with the participant in a timely manner about an action he or she performed or the state they are currently in. There are many participant interfaces. However, there are 4 classes that compose the most common interactions a user has with our platform. The self-report prompt, as you saw earlier, is either participant-initiated, or we use a very similar mechanism through biomarker-triggered confirm refute. The EMA system provides a flexible way to deliver various EMA-style questions to participants, and the EMI, or Ecological Momentary Intervention system, offers us a way to engage participants either through custom applications, as shown on the screen, or by calling any commercially available app. Finally, the privacy controller gives participants direct influence over what data should or should not be recorded in the system. And this was demonstrated in the demonstration earlier. But participant attention is in high demand, and the system should manage the burden we place on them. So to account for this, mCerebrum uses a bipartite graph design that fulfills all of the previous study requirements. In addition, our design supports dynamic adaptation by utilizing the user response, or lack thereof, to meet study requirements with a gradual relaxation of constraints while addressing participant burden constraints. In this figure, the diagram, the inputs column enumerates all of the possible choices available in mCerebrum. This includes burden constraints, privacy constraints, the start of the day, end of the day, various timing constraints, or the context, data quality, battery levels, so on and so forth. These inputs are mapped in completely arbitrary ways to a set of actions or controllers, and this is defined as part of a study protocol. Ultimately, the output of an action or controller results in a feedback mechanism back to the input column, and that allows us to adapt the system based on however a user handles the outputs or does not use the system. In some context, let's say I'm driving, maybe I deliver an EMA and I'm driving a vehicle, I shouldn't answer it. So me as a user, I don't answer it. Well, the system learns from this behavior and will in the future attempt to not deliver that EMA while you're driving. In another context, maybe we're concerned about the start of the day for prompting. Most studies that we are involved with right now require us to only prompt a participant from when they say they started their day to when they say they ended their day. While the system may record data beyond those time blocks, it is important to us to not deliver EMAs or EMIs or any other prompts outside of the prescribed period. And then we can also incentivize based on data quality. You saw this in the demonstration. This is, again, one more aspect to the burden management. So more generally speaking, though, mCerebrum is a system of high modularity built on a layered architecture. The applications that interact with sensor hardware generally cover a communication interface and data source layers. All of these applications we have developed, and these can be extended pretty much at will as we add new sensors to the platform. Every application in the system communicates through a common data router via DataKit, which also handles the storage interface and cloud communication. This information is shared through a signal processing layer where applications generally they compute biomarkers or do visualizations like the plotter you saw exist. The next kind of piece of the puzzle is the biomarker trigger block. And this really crosses from signal processing to participant interaction, where prompts that are generated from biomarker computations can be ultimately delivered to the participant. And the last layer, participant interaction, is where most of the applications that you've experienced in the demo and been shown in the slides today exist. So in total, there's about 2.7 million lines of code that make up all of these applications. And to date, there's at least 25 applications in the system, and this number seems to be growing week by week and month by month as we add new capabilities. However, this diagram really doesn't demonstrate the configurability and expressiveness of the system. So by grouping portions of the mCerebrum application ecosystem into categories, such as the core, prompts, engagement, biomarkers, and the kernel, and we coupling this with various health targets, study sites, and sensor platforms, we get a sense of the interconnected nature of all of these components. So for example, a study run with Ohio State involves many of the sensor platforms: smartphones, AutoSense, MotionSense, EasySense, so on. Various engagements, in this case, we're concerned about medication adherence. We have EMA prompts. So all of these things are linked to by the red and green lines. There's another way to look at the relationships, though, is maybe we're concerned about a biomarker, puff marker, for example. Puff marker is used in various studies: Northwestern, Rice, Utah, Vermont, Johns Hopkins. And it uses some key capabilities. It uses the utilities and DataKit API components of the mCerebrum core. So this kind of illustrates how all of the pieces interact with all of the others. And there's been a lot of work that has gone into this process. And we only have a small development team here in Memphis, but there's a lot of individuals. This is to name as many as we could possibly think of, had some role in the design, the development, and or the testing of this platform. So to date, over 951 requests for features or bug reports have been made to the development team. It is likely larger because I haven't updated this in the last week. I personally would like to extend my thanks to all of the individuals for their contribution to this platform. This work is supported in part by 9 separate grants from both NIH and NSF, and there are 4 supplements to these grants to enable additional studies. Furthermore, we're collaborating with other researchers to explore how mCerebrum can help their projects. So how do you begin? If you want to try this out, there are some requirements, in particular an Android phone running 4.4 or greater. Optionally, if you have a Microsoft Band, even though they're discontinued, we still have support for them, or Android Wear devices are going to be as part of the system soon. Also, the MotionSense HRV platform that was developed by Emory at Ohio State should be available near the end of summer for purchase. So you can incorporate that, which is one of the key sensors we use in our studies. If you're looking for step-by-step instructions to get started and even to replicate the demo we showed, this is the website you can go to. And Brian Ahern, one of our writers here, has done a great job with the site. And then if you have any questions, we encourage you to post them on our discussion board, which is available on discuss.md2k.org. If you want to learn any more, you can go to our website, md2k.org. The software documentation and overview are available at the docs site or the how-to site. There's always the email address. And just to recap, there are future webinars and tutorials. We will be giving webinar number 2 in this series, Conduct a Study, sometime in August of this year, following that up with Analyzing the Data in September. And then we will develop a tutorial for building mCerebrum applications, which should be available in the October timeframe. So if you wanted a hands-on guided session with the mCerebrum platform, we would be glad to arrange a separate webinar. All you have to do is let us know by sending us an email at that address, info@md2k.org, And once we have a critical mass, we will arrange for that to happen. So I'd like to thank all of you for taking the time to learn about mCerebrum, and we'll invite in questions at this time. So let me just read one of the questions from the chat that I see. Is this platform only compatible with Android smartphone devices or iOS as well? Currently, the software is only available on Android. iOS is a target that we're going to start working for, I think starting this summer. I don't have a timeline on when we'll have that available.
Hello.
I can hear you.
So is this system at this point configurable to an inpatient unit need? Because most of the psychiatric inpatients, there's no kind of recording. You don't want, patients typically don't have access to any cell phones. So can every functionality on the Android device be turned off except its specified modules?
Absolutely. So one of the apps that we have is connecting the Android sensors to our system. It's obviously optional. So I think the platform is set up in a very flexible way to collect the data that you need for your studies. I do know that at Ohio State, we use this in the hospital setting for the congestive heart failure patients. We just power one of the sensors that we deploy in the field with it in a hospital scenario. I hope that answers your question.
Sure. Just the one thing that, because the inpatient psychiatric units typically are locked units, so patients don't have the flexibilities that they will have in other hospitalized areas. So, but
okay.
Thank you.
Yeah, if you have more, why don't if you post on the discussion forum, I think we can have a longer discussion about what your requirements are.
Okay, great.
And how our platform might be able to address that. How do you handle the synchronization between different devices? Right now, all sensors come down to the mCerebrum phone, the apps on the phone, where it is time synced on reception. And Monowar will stand here and correct me if I say anything wrong. So that's how we handle time synchronization. Once it's on the phone, it's in a common time base. So at that point, everything is the same. Question: what wearable device can I buy right now to collect data? That's a good question. If you have Microsoft bands, then they will work. Like I said, we're going to be releasing Android Wear support soon. So if you have any Android Wear compatible smartwatch, that will also be able to collect some data. And then as far as our own hardware, it should be released at the end of the summer. So MotionSense HRV will collect accelerometry, gyroscopic data, and a multispectrum LED sensor for measuring your pulse. Next question: how can you secure the data in transit and at rest at all points in the pipeline? All of our data sits inside of an encrypted. It sits on an encrypted phone. So we mandate for our studies that the Android device is encrypted itself. And then in transit, between applications, right now there's no encryption. It is one of the future points that we want to address. And securing the data within the cell phone, within the communication layers of the cell phone. As far as when it gets off of the cell phone, we handle this with standard web service, web-based security, TLS certificates, HTTPS, and then our cloud has its own encryption model. Yeah, phone encryption is a feature of the operating systems, in a very similar way to how iOS handles it. How is the data uploaded to the cloud for storage? Right now, we are looking at, in a given 2-week period with a set of sensors, we collect data at about 500 hertz that results in something like between 2 and 4 gigabytes of compressed data. All of that right now is synced every 15 minutes to our cloud. And right now, we don't see any battery implications on that one. We don't see any performance implications. So we're sending a few megabytes every 15 minutes. And we have data plans that we run across. So this is all across cell signals, not even Wi-Fi. We do have the option to upload data at night on Wi-Fi while you're plugged into a charger to mitigate any kind of data overages or power concerns you might have. Yeah, right now our studies are in fairly large cities, but like I said, we have the option to upload over Wi-Fi. We also maintain all the data on the cell phone. So even if there is no data connectivity for, let's say, a 2-week study, when that phone arrives back at a lab, it can then be synced to our cloud, acquiring all the data. You just lose a real-time monitoring aspect of that. That is something that we will definitely be talking about in the future in the next webinar. So we can talk about how we monitor ongoing studies in the field.
Now, can I ask a question now?
Yes, please.
Okay, so the data that you upload to the cloud, is it in the raw format and then needs to be processed to make it like this is sleep related, this is the step count, all of that, or is it already processed data so that we can look?
Yeah, absolutely. We upload both. We upload everything we process on the phone, all of the biomarkers we compute in real time, stress or smoking or activity, driving, as well as all of the raw data. So the point of our cloud system, and this will be talked about in the third webinar, is to have all of the data there so we can do population scale analysis.
Now, and can the data, if I collect on my study, can I download it for the analysis in my own software as well?
I'm gonna answer the question, and then let's come back in September and go through the details. Yes, you'll be able to download the data. Okay. So please come back in September, and we'll go through a very detailed explanation and demonstration of how that works.
Okay. Thank you.
The data is also accessible from the phone itself, so you don't even need the cloud to begin using our platform.
Oh.
I'm trying to pick and choose questions here. Is the data uploaded on the cloud publicly available to other researchers? The answer to that one is no. These are all subject to the IRB consent process data sharing agreements that every individual researcher controls. So our data is private to us. Right now it's set up so that it's private to the study. So for example, at Northwestern, they'll be running about 225 participants. That data will be accessible only to the authorized users of it, as subject to IRB constraints, institutional agreements, data sharing agreements.
Tim, there are a few more questions about what is the cost to use this?
Yeah, I'm trying to parse all these as they go flying by. What is the cost to use the platform? The software is open source. You can go to our GitHub page, which you can find via the links. You can download it today, and you can use it for your own purposes. You can modify it for your own purposes. If you need access to the cloud services, that code will also be available. But I'm not going to say too much more until September, when we have a much nicer release available.
Do we need to manage a private server?
Do we need to manage a private server? We are working on options where there might be a way to, one, use AWS. Number two, you might be able to purchase a pre-configured system where you will have Cerebral Cortex pre-installed. You buy the platform, it comes, you plug it in, and it's good to go. If you want to manage a private server, the cloud software will be available open source, and you can install it however you would like. Can the software collect real-time data from multiple devices via both Bluetooth Classic and Bluetooth Low Energy concurrently? The answer to that one is absolutely. We do that with the Microsoft Band, I think. Microsoft Band is a Bluetooth 4 device, which we're currently running that concurrently with a Bluetooth Low Energy Motion Sense Band and Bluetooth Low Energy Omron devices. So we have no problems with that.
Another question is
about EMAs and EMIs. What is the mechanism in mCerebrum to pop out EMA, EMIs? How are tasks scheduled? I'm going to punt that to Monowar.
So we developed one application like EMA scheduler that actually, if you and one configuration file, so you can decide how can you trigger the participant, when to trigger. So in a configuration file, you can just write a rule there, and the EMA scheduler actually reads that file and trigger accordingly. So basically, how to configure the EMA scheduler, we'll discuss about these things on August 2017, whenever we discuss about the contract case study. But it is pretty much flexible. That means for any type of event, if you want to trigger the EMA or EMI, and also if you think that, no, I don't want to trigger in this case or in that case, so you can configure those things by just changing the configuration file. And EMA or EMI or what type of application that will open at the time, that is flexible. That means you can also open any commercial application or any survey application. You can add open those application, and you can just mention those things in the configuration file, and the system should work.
So how many sensors can connect to the app at one time? We have tested the system up to how many hertz from the paper?
Uh, 4,500.
So about 4,500 hertz. We know our platform, at least on a Samsung S5 phone, which is an older phone. We know it can record that amount of data. So specifically to how many sensors can connect, it's going to be subject to the resource limitations of probably a phone. To date, we've run, I don't know, 5, 6, 7 concurrent sensors. And you also have to understand that like motion sense reports multiple sensors, accelerometry times 3 axes, gyroscope times 3 axes. So I don't think there's a fundamental limit. It's just going to be a limit to what the devices themselves can handle. Is there a particular type of Android phone is recommended? We are currently using Samsung S4 and S5 series phones. However, that's for a very specific study requirement that we have. Our AutoSense device uses the Ant Plus radio platform. And these are some of the only phones with removable batteries that have the Ant Plus radio. As we move forward, though, we're getting away from this hardware technology and moving to Bluetooth Low Energy. So from my perspective, any reasonable smartphone, modern smartphone that supports Bluetooth Low Energy will likely suffice for almost all of our purposes. Is the app running 24/7 on the phone? And by app, you mean the mCerebrum app ecosystem. We do run it 24/7. We've taken the approach with our studies to not turn off data collection in an effort to avoid any problems with starting and stopping subsystems. That's not to say we can't do that. We have the ability to start and stop things. We found that the energy use, at least in our scenario, is low enough that we can run that 24/7 on the phone. Some of the apps run in the background. Some of them run in the foreground. One of the concerns we have right now, and this is fundamental to the way smartphones work, Android and iOS, is they have a quality of service module that likes to shut down applications that use too many resources. So one of the things that mCerebrum does is it attempts to monitor its own applications and restart them in the context or in the case that the OS shuts them down. We also have approaches that move apps to foreground threads, and these are generally reserved for critical systems: the EMA scheduler, the real-time signal processing, and the sensor data acquisition. We hope in the future that the resources will be a little more abundant and we can get away from that. But that's going to require some changes to both Android, iOS, and even the hardware capabilities of these devices.
I have one more question about the data that resides on the Android phone. So you said that it does not need to go up on the cloud, and we can just use that data. So now the data can it be exported to, say, Windows environment for further analysis, or it has to be an Android device and stays there?
No, absolutely. We export this routinely. We have a tool that extracts the data from the phone. There's a database file, and then there's a bunch of compressed archive files on the device. And like I said, we're happy to discuss this more in detail in the Analyze the Data webinar, or this can be handled on the discussion forum, the specifics about how to go about getting the data. I believe we already have instructions up there on how to extract it. So if you go to the discuss@md2k.org, you'll find these instructions. But essentially, the data shows up as CSV files, and one per data stream. So you can analyze that in whatever tool you would like on whatever platform you would like.
Okay, great. Thank you.